In this section, we will be studying improper integrals. So first, let's talk about the two things that make an integral proper. So what I mean by that is we've seen lots and lots of examples where we've evaluated definite integrals across some interval from a to b. We did require that that interval was finite. All that means is it had a definite starting point at some number a and an ending point at some number b. We also have the requirement that the function f of x that we're integrating is continuous on that interval a to b. Because if it's not continuous, then how are we going to find the integral of it from a to b? So if one of these two things is not true, then the integral would then be improper. So there's two ways we could get an improper integral. One of them is if the limits are not finite. Well, if the limits are not finite, they would be infinite. So if we have positive infinity or negative infinity as one of our limits on our integral, we know that we will be working with an improper integral. The second way is if the function is not continuous over the interval from a to b. So if we have an integral that goes over a discontinuity, it will also be improper. So let's consider the integral from 1 to b of dx over x squared. Before I even start thinking about how to integrate that, let's think about what that integral means. The graph of 1 over x squared. So by the way, the only reason I said 1 over x squared is because this is the same thing as integrating 1 over x squared, dx on the end. So the graph of 1 over x squared looks like this. There's a piece on the right side and a piece on the left side. And if we're integrating from 1 to b, then I'm saying from the x value of 1 to the x value of b, we're finding this area right there. That's what that integral represents, the area under the curve from 1 to b. So let's evaluate that. We're integrating from 1 to b, x to the negative 2 dx. We'll increase the exponent by 1, divide by our new exponent, and we evaluate this from 1 to b. I first plug in my upper limit of b, which gives me a negative 1 over b. And then I'll plug in my lower limit of 1, which gives me a minus negative 1 over 1, leaving me with 1 minus 1 over b for the answer to that integral. Now let's consider what happens if we let b go to infinity. So if b goes to infinity, then this integral can be interpreted as what? So if I let b go to infinity, I'm not going to stop my region there. Then this area just goes on and on and on and on and on and on and on forever because b is going on to infinity. So what we have represented in red then is the unbounded area under the curve for x greater than or equal to 1. There's the x value of 1. We're taking all of the x values that are bigger than it, and we're finding the area under that curve all the way out there. So that's what happens when we start introducing these infinite limits. If I consider, well, what happens if b is going to infinity? Well, remember, we actually did evaluate the integral. We did. We saw that the integral is equal to 1 minus 1 over b. So let's take the limit as b goes to infinity of 1 minus 1 over b. Well, the limit as b goes to infinity of 1 is 1, and the limit as b goes to infinity of 1 over b is 0, so this is equal to 1. So what we've actually just found is that all of this red area right here, that infinite area, is really equal to 1. That's the area under the graph of 1 divided by x squared from 1 to infinity. So we can interpret this as the area of this unbounded region. So this is what we just said, that area off to the right in red is equal to 1. So now let's talk about how will we in general define improper integrals when we have infinite limits. So when either positive or negative infinity is one of the limits in our integral. So let's say we have a function that we know is continuous from a to infinity, and I want to integrate it starting at a and going off to infinity. The problem is that infinite sign in the limit, in that upper limit. So what we do is instead, we don't integrate from a to infinity, we integrate from a to b. Notice I did leave space in front of that integral. And I'm going to let b go to infinity. So essentially, you just take the infinity sign that's up there and you replace it with b, and then you introduce a limit and say, okay, well, we're going to let b go to infinity. Very similarly, if we had a negative infinity as a lower limit, I would introduce maybe c and let c go to negative infinity, and I would let c be the lower limit on that integral. So the difference down here is I replaced the lower limit of negative infinity with c, and I introduced a limit that sends c to negative infinity. If the improper integral exists, if we're able to get an answer, then we say that the integral converges. Else, if we do not get an answer, it diverges. So for example, if we're getting answers like infinity, that does not exist, or negative infinity also does not exist, then it would diverge. So when we say here, if the improper integral exists, it needs to be a real number. Infinity is not a real number. And finally, if I wanted to integrate from negative infinity to positive infinity, I would need to split that up at some real number c. There's usually a convenient number to split it up in. So I went from negative infinity to c, and then I go from c to infinity. And both of these limits individually would fall into either case 1 or case 2. You can see that this second one here is a case 2, since it has the negative infinity as the lower limit. And this last one here is a case 1, since it has that infinity as an upper limit. So we would need to introduce limits to evaluate both of those. Now let's look at an example. Example 1, we want to evaluate this integral. I have a typo on here. I mean this to be the integral from 1 to infinity of dx over x. So first things first, now that I have corrected the integral, it is this infinity sign right there that tells us that this integral is improper. That's why this is in 8.8, because we cannot have these infinite limits. So what we do is, instead of writing the infinity, I no longer write infinity. I'm now going to write the integral from 1 to b. I'll keep everything else the same. But since I replaced the infinity with a b, I need to introduce a limit that's going to let b go to infinity. And now I'm just going to evaluate this as normal. So I have the limit as b goes to infinity. We know how to integrate dx over x. It is natural log, absolute value of x. And then we need to evaluate that from 1 to b. So we begin by plugging in our upper limit of b to have natural log b, and subtract and plug in our lower limit of 1. Natural log of 1 is equal to 0, so we get nothing there. So we need to know what is the limit as b goes to infinity of natural log b. Well, natural log is an increasing function. Natural log function looks like this. As b goes to infinity, as x gets really big, the function also gets really big. It keeps increasing, going up. So this limit is equal to positive infinity, which does mean that the integral diverges, because we did not get a real answer. Example 2, we again have an infinite limit. That right there is why our integral is improper. And so to evaluate this, I'm going to introduce a limit and let b run to infinity. And then I will integrate from 0 to b of e to the negative x dx. The integral of e to the negative x dx is negative e to the negative x. And we will evaluate that from 0 to b. So we have the limit as b goes to infinity of negative e to the negative b minus negative e to the 0. I'm going to rewrite this just to make it a little bit easier for us to evaluate. This negative sign in front is just like a -1. The fact that we have e to the negative b is going to send the e to the b to the denominator with a positive exponent of b now. So I'm just rewrote that negative exponent in the denominator. The minus sign in front is the -1 you see in the numerator. And then here we have a plus sign because we have two minuses combining right there to give us a plus. And anything to the 0 power is equal to 1. So now let's actually apply our limit. As b goes to infinity, this denominator is going to go to infinity, which means that entire fraction will go to 0. When the denominator gets very large, the entire fraction goes to 0. And so this integral is equal to 1. And so I can conclude that this integral converges because it does exist and it did equal a real number. Example 3, we again have an infinite limit on our integral, so we are going to introduce b. We're going to let b run to infinity, and we're going to integrate from 0 to b of 1 over x squared plus 1 dx. This is one of our inverse trig rules, so this goes back to 5.8. That rule fits this shape right here, where a is equal to 1 and u is equal to x. So that integral is the integral, comes out to be arctangent. So we have the limit as b approaches infinity of arctan, or tan inverse of x, that needs to be evaluated from 0 to b. So we begin by plugging in our upper limit of b. So we have tan inverse of b, and then we subtract and plug in our lower limit of 0, and we have tan inverse of 0. So what happens to tan inverse as x gets very large, as b gets very large? This is going back to 172. If you remember what the graph of tangent inverse looks like, the graph of tan inverse has a domain of all real numbers. Goes off to the right forever and off to the left forever, but it does stay bounded between those two horizontal lines. It never gets higher than pi over 4, and it never gets lower, it never gets higher than pi over 2, and it never gets lower than negative pi over 2. That goes back to 172 and inverse trig, and what did we restrict the domain of tangent to be? There's a little 171 tied in there too, but we're able to combine all that to conclude that the limit as b approaches infinity of tangent inverse of b is pi over 2. And then tangent inverse of 0 is equal to 0. And so our final answer is pi over 2, which is a real number, which does mean that the integral converges. Next, we're going to move on to look at how do we deal with improper integrals when we have discontinuities. So we've seen improper integrals where we had infinite limits, infinity showing up in our limits on our integration. Now we're going to talk about, well, what happens if the function is not continuous and the entire time that we're integrating over it. So the first case we look at are infinite discontinuities on the endpoints of an integral. So in this first case here, we're saying that the function is continuous on the interval a to b, closed on a, open on b, infinite discontinuity at b. So let's see what that looks like. So let's say A is here and B is here. If the function has an infinite discontinuity at B, I'm going to go ahead and put in a vertical asymptote at B. That's an infinite discontinuity. So the graph may look something like that, where it's shooting up to that vertical asymptote. So it's not continuous at B, but it is continuous from A to B excluding B. So if I were trying to evaluate this integral, that integral is this area. The problem is that there's a discontinuity at B. B is the problem in this case, that discontinuity. So what we do, how we handle that problem is we're going to introduce a limit. If B is an issue, I'm not going to write B as the upper limit anymore. I'll put C as the upper limit. I'll still keep A as the lower limit, and we're still integrating the same function d of x. But how do we want to approach C? We're going to have to introduce a limit. I do want C to approach B, right? Because that's really what it was supposed to be, but this is where we have to be careful. Because of this infinite discontinuity, we are only going to be able to approach B from the left, because the function is continuous on the left of B. So I'm putting this minus sign right there. Remember that notation. I'm taking the limit from the left. I could not take the limit on the right because I don't have anything to the right of B. I had that infinite discontinuity of B. On the flip side, let's say I wanted to integrate on an interval from A to B where A is excluded, and the function had an infinite discontinuity at A. Now my picture would look like a vertical asymptote at x equal A, and my graph would look something like this. So when I want to integrate from A to B, I want this area, which I'm allowed to do, but I'm not allowed to put A as a limit because there's a discontinuity at A. So what we're going to do is we're going to introduce a new value. I'll call it C as my lower limit. I'll keep B as my upper limit. We're still integrating f of x dx. But the question is, from what side are we able to approach C? Well, looking at the graph, there's nothing to the left of A, so I can't use the left. I would have to approach from the right side, so I'll put a plus sign on that. Well, not there, but when I introduce my limit, which I still need to do, I'm saying that this is the limit as C approaches A from the right, because it's not allowed to approach A from the left. So I still want to come in and approach A, but I'm going to have to approach A from the right side. In both of these cases, if the improper integral exists, then we say that it converges as before, else it diverges. In the third case, it deals with what happens if we're trying to integrate from A to B. Say A is here and B is here, but what if there's an infinite discontinuity in the middle at some point C? Well, we're just going to have to split this up into two separate integrals. I would need to integrate from A to C of the function f of x. Notice that in that integral, C is a problem. So you would need to apply a limit and approach C from the left in that integral. You would also need to integrate from C to B. In the second integral that I wrote, C is again a problem. There's a discontinuity at C. But in this integral, if you're going from C to B, you would need to introduce a limit and approach C from the right, since you have graph on the right side. And now let's look at an example. So in example 4, first we have to figure out, why is this integral improper? There's no infinite limits on here, but I do see that I have 0 as one of my limits of integration. Keep in mind, if it helps you realize what function you're integrating, we are integrating 1 over the cube root of x. So the fact that 0 is one of those limits of integration is a problem because there is a vertical asymptote at x is equal to 0. So what we're going to have to do is we're going to need to introduce a limit. I'm going to need to let b approach 0. We have to be careful about what side we want to approach 0 on. I'm going to leave that blank for now. Then I'll go ahead and write in the dx, or the integral that we have from b. I did change the lower limit. I replaced 0 with b to 1. And in here, I'll just go ahead and rewrite this as x to the negative 1/3 dx. Okay, so what you have to do when you get to this point is whatever this function looks like, I would just think, I'm trying to integrate from 0 to 1. We do know there is a vertical asymptote at x is equal to 0. So if we're trying to find area in here, from which side are we allowed to approach 0? Are we allowed to approach from the right side, or are we allowed to approach from the left side? We would have to approach from the right side. There is nothing on the left side. The area we're looking for is on the right side. So we're going to approach 0 from the right. And now let's actually integrate. We're going to increase our exponent by 1. So it will now be 2/3. And we will divide by our new exponent, which means we're multiplying by 3/2, and we will evaluate this from b to 1. We begin by plugging in our upper limit of 1, which would just give us 3/2, and then I will subtract and plug in my lower limit of b. And as b goes to 0 from the right, to b to the 2/3 goes to 0, and this entire limit equals 3/2. Let's look at example 5. In example 5, we again have this lower limit of 0, and we know that the function 1 over x cubed does have a vertical asymptote at x is equal to 0. So I'm going to have to redo this limit. I'm going to approach 0 from the right because I'm integrating from 0 to 2. I've replaced 0 with b, what we introduced the limit as, and we're integrating x to the negative 3. Don't drop the limit, not until you apply it. Increase your exponent by 1 and divide by your new exponent. And we're going to get ready to apply fundamental theorem of calculus now. So we first plug in our upper limit of 2. It may be helpful to rewrite this just so we're not looking at these negative exponents. So all I did was I just put that negative in the top, and because this was a negative 2, x to the negative 2, I sent that to the bottom. The 2 that was down there stayed down there the whole time. So that's what happened from there to there. So now let me start and do my evaluation. First, I'm going to, I think somewhere along the lines, I also switched my limits. First, I'm going to plug in my upper limit of 2, which will give me negative 1 over 8. And then I will subtract and plug in my lower limit of b. Be careful because subtracting a negative will turn into a plus sign. As b goes to 0 from the right, we need to think here. So the first term, as b goes to 0 from the right of negative 1/8, we're just going to get negative 1/8. But what happens as b goes to 0 of the right on 1 divided by 2b squared? Well, let's think about what 1 divided by 2b squared looks like. To be clear, we've applied the limit to the negative 1/8. Now I'm trying to apply the limit to the 1 over 2b squared. Don't let the b's confuse you. If it's easier for you to think of things in terms of x, you can think of them like this. I wouldn't write this as you actually do all of this work, right? Don't write this, but think of this when it's time to apply the limit. What does the graph of 1 over 2b squared look like? Well, the graph of 1 over 2b squared looks like that. If you were to graph it, it has a vertical asymptote at 0, and both ends of the graph shoot up. So what happens as b goes to 0 from the right? Well, here's 0. Here's the right side. As we approach 0 from the right, the function is shooting up to positive infinity. So that second part of the limit is infinity. So this entire limit equals infinity, which does tell us that the integral diverges. When we look at example 6, first we have to consider why is this integral improper? And it is improper because this function does have a vertical asymptote at x is equal to 0, which is between -1 and 2. I'm going to move this up a little bit. So what we're going to have to do is we're going to need to come in and split this integral up at that problem point of 0. So we'll talk about the integral from -1 to 0, and then we'll talk about the integral from 0 to 2. So starting with the integral from -1 to 0, 0 is still a problem. So with this first integral here, we're going to have to introduce a limit. I'm going to introduce the limit as b approaches 0 from the left, because I'm talking about from -1 to 0. It might be helpful to make a number line. Think about -1, 0, and 2 on the number line. In the first integral is where we broke it up from -1 to 0. So we're talking about this part on this integral. How can you approach 0? This is the right side, this is the left side. In the purple piece, you can only approach 0 from the left. So I will replace the 0 with b since we introduced the limit. And we have x to the -3 dx in there. And then in the second integral, I'm going to introduce a new limit. I'll call this the limit as c approaches 0. I'm working on the interval from 0 to 2. I can approach 0 from the right. So I'm going to let c approach 0 from the right. I'll replace the 0 in my limit with c. The 0 that's in the integral, this bottom limit of 0, I'll replace with c. Keep my upper limit of 2. And we're integrating x to the -3 dx. So now we have these two separate integrals that we're evaluating. I'm going to break off and just work with one of them to see what one of them equals, and then I'll go and work with the second one. If you ever have to split your limits, your integrals up, it's a good idea to work with your integrals one at a time after you split them up. So I have them split up on this first integral. I'm taking the limit as b approaches 0 from the left. I'll go ahead and integrate. I have x to the -2. I'm dividing by my new exponent. I'll go ahead and stick this x squared in the bottom. This needs to be evaluated from -1 to b. I'll begin by plugging in my upper limit of b. So I have -1 over 2b squared, and then I will subtract, which will turn into addition, since we have the minus sign in there. We'll plug in the lower limit of -1, which will give us 2 times -1 squared. Now let's actually apply the limit. What happens to the graph of -1 over 2x squared as we approach 0 from the left? So to help give us some perspective, off to the side here, I am going to graph -1 over 2x squared. Well, that graph looks like this. Vertical asymptote at 0 and both ends of the graph shoot down. So as we approach 0 from the left, get on the graph on the left side and approach 0, we go down to -infinity. So this entire limit is equal to -infinity because that shoots down to -infinity. So we've just said that this blue box right here, just this one integral, is -infinity. Well, if that's -infinity, then the entire integral diverges. it doesn't even matter what the second one equals. It cannot possibly mean that the sum of them will be a real number if the first one was negative infinity. So we can conclude that the integral diverges. In example 7, we have an integral that is doubly improper. And what I mean by that is there's two issues. One, there's this infinite limit of infinity, and then there's also the issue of 0, because this function on the inside is not defined as 0, not with that square root x in the denominator. So what I'm going to do to deal with those issues is I'm first going to pick a number to split this integral up at. So what I would like to do is I want to find some number, 0, I'm not putting anything there yet. I'm going to integrate from 0 to some number, dx over root x, x plus 1 plus, wherever I split it up at, I'll pick off again there, and then I'll go off to infinity dx over the square root of x times x plus 1. I want to take a second to first talk about what number we should put there. Technically speaking, I could put whatever positive number I want. So like I could say, when I look at this, if we're trying to integrate from 0 all the way to infinity, you could break it up at 2 if you wanted to, and say let's go from 0 to 2 and then 2 to infinity. Or you could move further along the line and say I want to break it up at 20 and say I'm going to integrate from 0 to 20 and then I'm going to integrate from 20 to infinity. None of those is wrong. The problem is that there's usually a best choice to make. And so what I want to talk about now is what's the best number to split this integral up at. So what number do we actually want to split it up at? And to do that, let's first see how are we even going to integrate this. So first, let's just talk about how is this going to integrate with this dx over root x times x plus 1. So if we try u sub and let u equal the square root of x, we see that that could take care of this square root in the denominator, but the problem is that it does not take care of the x plus 1 that's down there. But I could do a double substitution and square both sides of this to see that u squared is equal to x, which means that u squared plus 1 is equal to x plus 1. So I could substitute something in down there. Now let's go and see, well, what would du be? If u is root x, then du is 1 over 2 root x dx. Well, we do have a dx over root x in the integral. Multiply both sides by 2 to see that 2 du is dx over the square root of x. So now if we actually start substituting into the integral, all this dx over the square root of x can be replaced with a 2 du. And then this x plus 1 that's in the denominator, well, that's just u squared plus 1. And that is in the denominator. And we do know how to integrate the integral of du over u squared plus 1. We saw that rule earlier. It's an arctan rule. So this is 2 arctan u. I'll put a plus c just because I don't have limits on this integral. And let's not forget that our u was root x. So we got 2 arctan root x. Now that I know what I will get when I integrate, I can think about what is a good number for me to split the integral up at. For example, I don't want to split the integral up at 5 because I have no idea what arctan of root 5 is. And at some point I will have to evaluate that. So very conveniently, I'm going to choose to split the integral up at 1 because I do know what arctan of 1 is. So now that I've chosen what number I'm going to split the integral up at, I'll go ahead and introduce my limits. This first integral has an issue at 0, so I'm going to approach 0 from the right. Replace my lower limit of 0 with b. Mind you, we do already know how to integrate all this, but I'll write that in the next step. And this second integral has an issue at infinity, so I'm going to introduce c, integrate from 1 to c. So now let's actually apply our integration. We know this integrates to be 2 arctan square root x. In the first one, I dropped my limit. Don't make that mistake. We're not ready to drop the limit until we apply it. So the limit is still there. We know the first one comes out to be 2 arctan root x. That needs to be evaluated from 1 to b. The second one still has a limit of c going to infinity in front of it. Also equals 2 arctan root x. Needs to be evaluated from 1 to c. So starting with the first one, when I plug in my upper limit of 1, I have 2 arctangent of square root 1. Square root 1 is 1. Minus 2 arctan of root b. Plus, in our second term, we have the limit as c approaches infinity. I'll plug in my upper limit of c. So we have 2 arctan root c minus 2 arctan 1. Plugging in our lower limit of 1. Square root of 1 is still 1. Okay, so arctangent of 1 is pi over 4. So we have 2 times pi over 4 right here. Apply the limit to that, it's still just 2 times pi over 4. The limit as b goes to 0 in the arctangent function will be 0. So this is minus 2 times 0. The limit as c goes to infinity in the arctangent function is pi over 2. So we're on this term now. We still have this 2 in front. As c goes to infinity here, we're going to pi over 2. I wrote pi over 4 in this first one. That's correct. Over here, yeah, be careful. Arctangent of 1 does equal pi over 4. Over here, when you take the limit as c approaches infinity and you apply it to arctan root c, that goes to pi over 2. So we have 2 times pi over 2 right there. And then minus 2 arctan of 1. Arctangent of 1 is pi over 4. So our first term and our last term are going to cancel each other out in this integral, leaving us with simply 2 times pi over 2, which is equal to pi. In our last example, our integral is improper because of the lower limit of negative infinity. Everything else in the integral is continuous. What we will have to be careful with is how to actually integrate this. So I'm going to leave some space here, leave blank space there. But when we actually get time to deal with the improperness of this integral, I know that I'm going to introduce a limit. I'll say the limit as b approaches negative infinity, and I'll replace that problematic lower limit with just a b. So at this point, we then need to be concerning ourselves with, well, how do we actually integrate this? And to integrate that, we're going to have to use integration by parts from section 8.2 that tells us that the integral of u dv is uv minus the integral of v du. Using LIATE, I do not see a log, I do not see an inverse trig, I do see an algebraic expression. I will let u be x. dv will be everything else in the integral. I will differentiate u to get du as dx, and I will integrate v to get negative 1/4 e to the negative 4x as v. And now I will apply uv minus the integral of v du to give me negative x over 4 e to the negative 4x. From that, I add, because v is negative, the integral of 1/4 e to the negative 4x dx. We do know how to integrate that. The integral of e to the negative 4x is negative 1/4 e to the negative 4x. So that'll give us a negative 1/16. I'll put a plus c here. I won't when I go down there because I actually do have limits, but we have integrated it now. So now I can come down here and say, oh, well, I need the limit as b approaches infinity of negative x to the 4th e to the negative 4x minus 1/16 e to the negative 4x, which needs to be evaluated from b to 0. So I first plug in my upper limit of my upper limit of 0. I would have 0 minus 1/16, because anything to the 0 power is 1. I need to subtract and plug in my lower limit of b. When I subtract, this minus sign will become a plus. We'll have b to the 4th e to the negative 4x. Other minus sign will become a plus. Not e to the 4x, but e to the negative 4b. E to the negative 4b, because I'm replacing x with b. All of this still has the limit being applied to it. And I'm going to rewrite those e to the negative 4b's as e to the 4b's in the denominator. Because when you put them into the denominator, I hope it's easy for you to see that as b goes to infinity, that denominator gets huge. So this whole term goes to 0. This denominator gets huge, and so that entire last term goes to 0. And all that's left is a negative 1/16.